So today we will discuss about the floating point representation. The floating point representation speaks about different concepts like how to represent a number, and that is real number in a floating point. So the floating point means it can have both integer part and fractional part as we discussed, but the only thing is that if let's take a number 123.156, so this is called a real number. So the real number, why it is called real number? Because it has two parts. One is integer part and this is called fractional part, and these two are separated by this decimal point. So once again I am repeating, if you take the number, this is our number, and in general this can be a number and this also can be a number. The first one is called an integer, and you all know that integer doesn't have any fractional part, or you can say it has zero fractional part. So representing such type of integers can be done, in representing an integer can be done in fixed point or a floating point. There is no difference in representing 110 in fixed point or floating point. Both representations are same with respect to integer, but the only differ in when we have a representation when it is required to represent a real number. As the name specifies, the real number contains both fractional part and integer part. Let's take an example, 123.115. So this 123 is an integer part, 115 is a fractional part, and this is called decimal point. So the decimal point is after 3 digits of the integer number. And if I want to represent such real number in computers, how to store, the first doubt as a computer science student is how to store this particular number in computer memory. How the real number can be stored in computer memory. For that we have different techniques, and first we should know how this real number can be represented. This real number can be represented in two notations. One is fixed point and floating point. Already we discussed about fixed point. I will just recap in brief way how to represent fixed point number. What is meant by fixed point? Fixed point says it has fixed number of bits. Let's assume 15 bits are reserved for specifying integer part, and let's assume 16 bits are reserved for specifying fractional part, and 1 bit is reserved for sign bit. So this is the format of fixed point representation. So it has fixed number of bits reserved for integer part and fixed number of bits reserved for fractional part. By this way, what's happening, the decimal point or binary point, let's assume this is 1 bit, 15 bit, 1 bit, for a total of 32 bit. If the total width of the word or memory location is 32 bits, then 1 bit is reserved for sign bit. Remember, sign bit 0 means it is a positive sign, sign bit 1 means it is a negative. So do you think the decimal point or binary point is, the position of the binary point is fixed? Yes, the position of the binary point is fixed in case of fixed point representation. So if someone asks you in fixed point representation what is fixed means, you can say the number of bits for integer part of a real number, and on number of bits, say this is a real number, and the number of bits for real number, number of bits for fractional number is fixed. By this way, binary point is also fixed. So here what are the things fixed means? The number of bits allocated for representing integer part is fixed. Similarly, the number of bits allocated for a fractional point is fixed. By this way, the binary point is also fixed. So this is called fixed point representation. The disadvantage here is that the binary point is fixed. That is itself disadvantage. Why it is disadvantage? This fixed point arithmetic, that means if you represent two numbers, let's assume 123.115 and 110.116, if you want to multiply this, it is very complicated. Rather than this, if you say 1.23115 into 10 power 2 multiplied by 1.110116 into 10 power 2. If you convert these numbers into this notation, it is quite easy, or you can guess that the value 1.2 and 1.1. 1.2 and 1.1. So 1.2 multiplied by 1.1, or you can say 12 into 11 by 10 into 10 into 10 power 4. So doing arithmetic is quite complicated in case of fixed point arithmetic. The solution is, if you convert into the number a format which can be easy for doing computation, it is called, then the computation would become very easy. So such conversion is called, another notation, famous notation called floating point representation. So the floating point representation, what it says in brief, it simply converts the floating point. I'll explain what is important. Now we understand that doing fixed point arithmetic, fixed point arithmetic is difficult. So if you convert these real numbers into some numbers like 12.3115 into 10 power minus 1 and 11.0116 into 10 power minus 1, then you can do the calculations comparatively less amount of time, or it would be less complicated if you convert these real numbers into this notation. So this representation is called floating point. So by this time you should understand that floating point notation, the position of a binary point is not fixed. So the position of a binary point is not fixed. By this way, the position of a binary point is not fixed. So whether it is an advantage or disadvantage means, yes, of course, definitely it is an advantage. So before learning a concept, why we have floating point representation when we have already one representation called fixed point, what is the importance of knowing or learning another representation such as floating point is very important to understand the reason behind knowing about floating point representation. I think by this time we should have an idea that doing, yes, a real number can be represented in fixed point, but it is a problematic. That means, in the sense, it takes more time to perform fixed point arithmetic operations such as addition, subtraction, multiplication, and division. Performing these operations on the numbers which are represented in fixed point is quite complicated. Complicated in the sense it consumes two of the most important resources in computer memory. Remember, in computers, execution time is the costliest resources, because the execution time means utilizing the CPU time. The goal of any computer program or a system program is that it should utilize less amount of CPU time and use less amount of memory. But there is always a balance or trade-off between the memory and CPU execution time. That means if a program is taking more CPU execution time, then you can understand that it is taking less amount of memory. Or I can say in reverse manner, if the CPU execution, if a program is taking or consuming less amount of CPU execution time, that means it may take some large amount of memory it may require. In the same way, vice versa also applicable. That is, if your goal of the program, or if you design a program such a way that it uses less amount of memory, that means it will take more execution time. So the programmer should always remember that write a program such that always use optimum number of execution time and optimal memory usage. Optimal in the sense there should be a balance. It should not use too much of memory, or you should not use very less amount of memory. What happens if you take less amount of memory in the process of designing a program which uses very less amount of time? You may be executing, you may be consuming more amount of CPU time, which is not at all acceptable. Similarly, if you are writing a program which uses very less amount of execution time, in that process you may be consuming more amount of memory, which is also not acceptable. So there should always exist a trade-off between the memory and CPU execution time. So the goal is, when it comes to fixed point representation, yeah, as I said, it takes more amount of time, that is complex operations, arithmetic operations, performing the arithmetic operations on numbers which are in fixed point representation are more complicated. So to make it simpler, so when I say it is more complicated, it might be complicated in terms of the memory usage or CPU execution time, or in both of them. That means it may consume more execution time, may be taking more execution time, it may be taking more amount of memory. So just to reduce this, we have another representation that is called floating point representation. So this is the reason behind learning or having another representation for real numbers. So I hope everybody understood the real meaning of floating point representation. As I said, the binary point, the position of the binary point is not fixed. First you should remember. So when I say the binary point, the position of the binary point is not fixed, then there is no hard rule that, or there is no thumb rule that these number of bits should be represented for integer and these number of bits should be represented for fraction. There is no point like that. So the binary point can be at extreme left or extreme right or in the middle. So just keep in this mind. But the goal is you should have the binary point at such a position that the arithmetic operations can be done in easy manner. So the floating point. So now we'll discuss in detail about floating point representation. This representation or floating point representation doesn't reserve a specific number of bits for integer part or the fractional part. Like I said, there is no hard and thumb rule that these number of bits should be allocated for integer part and these number of bits should be allocated for fractional part. It is not fixed. Instead, it reserves a certain number of bits for the number called mantissa and a certain number of bits to say within that number where, so it reserves a certain number of bits for the number called mantissa. So here comes a word called mantissa and a certain number of bits to say where within that number decimal places sits. So a certain number of bits to say where here within that number the decimal place sits called exponent. So there are two words, mantissa and exponent. So the mantissa represents some number and exponent specifies the position of the binary point in that number. So once again I am repeating, floating point number, we don't call it as integer part or fractional part as we specified in fixed point. Instead, in floating point we have two parts, one is mantissa and other is exponent. So the mantissa contains a number. What is it number? It is a fixed point number. Fixed point, in fact it is a fixed point integer, and the exponent says the position of a binary point within this number. So I will give an example. What is this fixed point and floating point? The floating point representation, the floating point representation of a number has two parts. The first part represents a signed fixed point number. The first point represents a signed fixed point number called mantissa. The second part of the designates the position of the binary point and it is called exponent. The fixed point mantissa may be fraction or an integer. The fixed point mantissa may be a fraction or an integer. I will give an example. Let's take a simple example. 12.25. Now if I want to represent this in a let me take a simple example, 1.25. Let's take, this is a number, so the same number can be represented in 125 into 10 power minus 2. So this 125 is called mantissa and minus 2 is called exponent. What this minus 2 specifies, did you remember? It represents that the position of the binary point from rightmost digit. So in 125, from this 10 power minus 2, one can imagine that the position of the decimal point is two positions from rightmost position, like 1.25. So this is the real meaning of representing a number in fixed point. So here 125 is called mantissa, 10 power minus 2 is called exponent. This mantissa can be plus or minus, so it can be a signed fixed point number. What is trying to say, sometimes I can represent the same number as 0.125 into 10 power 1, 10 power 1. So in mantissa part what you write, again 125. In exponent point I will write plus 1. This is plus 125. So it is very really easy. It is very necessary to understand this point. That is, I can represent this 125 like I'll give you a simple example. Simple 1.25. So I can represent 125 into 10 power minus 2. So this is plus 125. Store this plus 125 in a mantissa position, and this is minus 2. This is called exponent. So mantissa will also have the sign bit, and this is called exponent, and this is called mantissa. So the exponent also should have the sign bit, mantissa also should have the sign bit. So this is one way of representing, and you can imagine that here mantissa is again a fixed point number. There is also another representation for the same this 1.25 in different notation. For example, there are n number of notations for this can be done 0.125 into 10 power 1. So in this case there is a plus, sign of the mantissa is plus, again it is 125, in exponent it is plus and it is 1. So this is called mantissa. This is sign of the mantissa, this is sign of the exponent, this is the exponent. Remember, exponent specifies the position of a binary point or decimal point. So you may get a doubt. So like that there can be n number of representations for a floating point number. So there should be a standard procedure, standard way of representing a real number in floating point. There comes the concept of normalization. I will explain in brief what is normalization means. Normalization means if you take any real number, like let's assume 11.25, it should always represented 1 dot mantissa into 2 power minus e. This is called the standardized or normalized way of representing any floating point number. So here m is called mantissa, e is called exponent. Moreover, the most significant bit MSB of the mantissa should be non-zero. Remember, these are the two important rules when it comes to standardizing way of representing a floating point number. What is that? Let's take the same example. We should convert into 1 point something, right? So 1 point, I can write it as 125 into 10 power 1. So you won't represent this one, you just represent this 125 and sign bit is plus and plus 1. This is the shortest way of representing a floating point number. Now we will discuss in detail about this. So only the fixed point matrices may be fraction or integer. And next thing is, floating point is always interpreted to represent a number in the following form: mantissa x radix e. The mantissa m and exponent e are physically represented in the register. A floating point binary number is represented in similar manner except that it uses base 2 for the exponent. A floating point number is said to be normalized if the most significant digit of the mantissa is 1. The most significant digit of the mantissa is 1. So the mantissa m and exponent e are physically represented in a register. Floating point binary number is represented in similar manner except that it uses base 2 for the exponent. A floating point number is said to be normalized if the most significant digit of the mantissa is 1. So this is about sign bit. This is called exponent. This is called mantissa. So the actual number is Naveen. So this is called sign bit. This is exponent part. This is called mantissa. So the actual number is sign bit, yes, and 1 plus mantissa or 1 dot m into 2 e power bias. So the exponent is in biased form. We will discuss in detail about what is meant by biased form. So see, the advantage of the biased form is that, as I said, the exponent also required to have some sign bit. So instead of so for removing the sign bit, we are introducing a concept called biased form. So what happens with this biased form is, it will using this biased form, if you this becomes a bias is an unsigned number, but you can interpret it as a sign. We will see how it is. Remember, bias is an unsigned number. It can be interpreted as a signed one. So that is the real meaning of biased form. We will discuss in detail. So S is the sign bit, M is the mantissa, E is the exponent value, and bias is the bias number. Note that the signed integers and exponents are represented by either sign representation or 1's complement representation or 2's complement representation. So you all know the representation called sign representation, 1's complement, 2's complement. Already we discussed this in the previous class. Remember, sign representation means it will have a sign bit and magnitude or integer part. Let's take 1101. is a number, and if it is 0, 110 means 13. If it is 0 plus 13, otherwise it is minus 13. If you take the same number in one's complement representation, 1101, including sign bit, so this is the representation for one's complement. In case of two's complement, you just add 1. This becomes two's complement, one's complement, sign bit. What are these? These are the representations of a number, of an integer number, how it is going to be stored in the memory. Next, note that the signed integer and exponents are represented by either sign representation or one's complement representation or two's complement representation. The floating point representation is more flexible. The floating point representation is more flexible. Any non-zero number can be represented in the normalized form. And the normalized form, for example, let's take we have a 32-bit number. That means the number can be represented, a floating point number or a real number can be represented in a 32-bit format. 1 bit sign bit, which is called sign bit, 8 bits for exponent, next 23 bits for fractional part or integer part. Then you should ask me a question. Here also we are fixed length for exponent, fixed length for mantissa. Yes, of course, but the point here is we are not fixing the position of a binary point. 22. The leading 1 bit is not stored, as it is always 1 for a normalized number and is referred to as hidden bit. Let's take a simple example that is given here. So here it is given that 53, the number is minus 53.5. When it comes to its representation, the actual number value of 53 is 110101 and fractional part is .1. So as I said earlier, you have to bring this fractional part to here. So you have to make 1.101011. Then to compensate this, since you moved the binary point to the left hand side, you have to say minus 1 2 3 4 5 positions. So the exponent value would be plus 5, just to compensate this. So this is the representation for normalized representation for 53.5. So 1, you can ignore this integer part, just you have to represent this fractional part 101011 with exponent part and mantissa part, right? So first, in this 32-bit, 1 bit is reserved for sign. Okay, number is minus, right? Minus 53. So 1 bit, 8 bits for exponent part. So 10 exponent part is 5, right? 101, and you can the remaining 5 zeros here, and represent this 101, 011 and zeros. Where this is the 8-bit binary value plus n. Note that 8-bit exponent field is used to store integer minus 126 to 127. So it is very important to know the concept called bias in floating point representation. So in floating point representation, the smallest normalized with 8 bits, you can represent minus 126 to plus 127 for exponent part. But how to get a positive number? If you do subtraction minus the by 2 power 8 means 256 minus of minus 126, you will get the value. This is called biased form. This is called the biased form. So the smallest normalized positive number that fits into 32-bit is 1.23 zeros into 2 power minus 126. That approximately equals to 1.18 into 10 power minus 38. With this you can understand that we can never represent a zero in a floating point number. What is the minimum floating point value for a 32-bit memory? Is that 1 point followed by 23 zeros into 2 power minus 126. This is the minimum number, minimum floating value for 32-bit. The smallest normalized positive number. The largest normalized positive number means 1.1111, 23 ones into 2 power plus 127. That value would be around 3.40 into 10 power 38. It's a very big number. And these numbers are represented as like this. This is the smallest number and this is the largest number.